I will go ahead and introduce the speaker. So today in person with us, we have Zezhou Cheng, who is a tenure-track assistant professor at the Department of Computer Science at the University of Virginia, and he leads the Computer Vision Lab at UVA. Before that, he was a postdoc at Caltech, and he has a Ph.D. in computer science from UMass Amherst. So Zezhou is going to tell us about computer vision for scientific discovery. So please take it away.
Hey, so hello everyone. Hello everyone. Thanks for having me here today. As Ryan said, I'm Zezhou, and the topic today is computer vision for scientific discovery. So today there are going to be two parts. First part, I'm going to give a very brief introduction to computer vision. What is computer vision and what kind of tasks we are working on, and the mission of Computer Vision Lab at UVA. So for the second part, I'm going to present our story on research in computer vision plus X. So the X could be ecology, migration, bird migration. It could be material discovery. Let's start from the first part. So what is computer vision? Our definition is we want to build a machine to see the 3D world. A very broad definition. And here is an illustration. So we are living in a dynamic 3D world. The world has many properties like 3D geometry, objects, and motion. What we have in computer vision is a projection of the 3D world to the camera field, which is a 2D image. And the 2D images consist of pixels, which are simply multi-channel array. And the mission of computer vision is to do the inversion. We want to convert light into meaning. So this is the mission of computer vision. The meaning could be many things. It could be geometry. It could be semantics, like the object categories. It could be the dynamics, like the motion, the action, and the transition over time. So this is a very broad definition of computer vision. So more concretely, there are many tasks in computer visions. If the input is simply an RGB image, then the task could be recognition. So we want to recognize what are inside this image. So it could be classification, it could be detection, it could be semantic segmentation. And another task is the classical computer vision task is 3D reconstruction. So from RGB image, our human has pretty good depth perception, 3D perception. There are depth estimation, surface normal estimation, and holistic 3D reconstruction. And many other tasks like segmentation, and more recently, a very hot topic in computer vision, image generation. So given this image, can we generate a new style of the input image? Okay, but besides the RGB as input, there are actually many other modalities, probably not everybody is familiar with. For example, we could have videos as input. Here I show two examples in my work. One is given a video of the car. Can we reconstruct the 3D shape like this rotating car? Another example is tracking. So given this video, we want to track every single pixel, the motion. I guess there might be some applications in other domains. Besides the image and the videos, we could also have 3D point clouds. If you have self-driving cars, some people use the LiDAR sensors, then the input to your model is going to be the point cloud. And if you have 3D point clouds, the task could be classification, detection, and segmentation, with wide applications in downstream tasks like robotics, self-driving cars, etc. But for both video and 3D point cloud, there will always be a generation task. So you can generate 3D shapes from the text, you can generate videos from text input, etc. So that means we are working on many different tasks in computer vision. There's one successful story in computer vision. We call it supervised learning. And here is a pipeline. So given a task or motivation, we want to collect some data and the labels. Depends on the task, the data could be different. For example, images, if your task is classification, then it's a single tag. Object detection, then besides the single tag category, you also have bounding box. Landmark detection, key points, 3D pose estimation, just the angles. So depends on your task, the data and the labels could be different. Then once we have the data and the label, we want to develop some models. And over the past decades, we have developed many neural networks. And we once we have decided the model, we train it on the data and the labels, and we evaluate on the test set. So it works well, then we move forward. If it's not working, we go back to earlier stage. Data and the label, collect more data, more labels, higher quality labels. That's what people are doing most of the time in industry. Then we could also do more model development. And everything, we're happy with everything, then we move forward. We do scientific discovery, we put it in the product, self-driving cars or robotics. So this is the pipeline, and this is also the pattern. I've been collaborating with people out of domain. So 5 stages and some examples. Image classification back to 2015, deep learning models had already surpasses humans' performance on this large-scale image classification, and instant segmentation, segment anything, try to group similar pixels together. So all of these successful stories rely on 3 pieces. So 1, large-scale 2D data set, images, videos, high-quality 2D labels, and supervised learning. Very stable, very mature pipeline. But there's the issue, the data and the labels. You're gonna see that this is always the core of deep learning. If you have more data, higher quality label, then you are in good shape. So this is also the challenge in many tasks. For example, if we have unlimited number of images or videos, that is true, but for other domains like satellite image, radar images, 3D data, they are very scarce. And as your task gets more complicated, the annotation cost and annotation noise gets larger. So we need to deal with these issues in many of our interdisciplinary research. And that leads to the topic of our computer vision lab. So the theme of our computer vision lab is to develop models to learn to see the 3D world with minimal human supervision. We want to minimize the human efforts. And some works from the data perspective, we develop models to learn from unlabeled images, from unlabeled videos, and the labels are noisy, so we develop model to learning from noisy labels. Here, one example is heterogeneous labels. We're gonna give more details later. And learning from coarse supervisions, if you don't want to spend so much time, you can just give a hint to the model and how to learn from these lower like coarse supervisions. It's also the topic in my lab. So model-wise, we want to really understand neural network theoretically. And we also design generative model to generate 3D shape, and recently, more recently, we generate videos. And applications, we've been working on computer vision for ecology to detect and track birds in weather radar data, and also collaborating with people working on chemistry for material discovery. So today I'm gonna focus on the application side and showcase how we collaborate with people out of computer vision. So that leads to our second part, our story on computer vision plus X. As a summary, in the first part, we discuss what is computer vision and the mission of computer vision lab at UVA. So let's start from the, let's discuss the second part. We'll showcase our effort on computer vision for ecology. So the project is about detect and track birds in weather radar data. And we're gonna follow this pipeline. So we start from the motivation and the task. The motivation is back to since 1970s, there are 2.9 billion birds has gone. So this is very sad, and this is the statistics from our collaborator at the Cornell Lab of Ornithology. Research is urgently needed to understand and reverse the causes of these declines. And to do this, we need to gather historical information, like in the past decades, of image of bird migration, habitat usage, and the effect of climate change on the birds. So, but it's very hard to collect this data because the birds are most of the time they're in the air. It's hard to detect them, to track them. But fortunately, we have weather radar data. So if you look at this, this is animation. These radar stations distributed over U.S. continent. There are over 140 radar stations. So they are originally built to monitor the weathers. But decades ago, ornithology discovered that they actually contains a lot of biological information. So if you look at the animation, you're gonna see some bluish blobs moving from the eastern to the western part. These are all birds during the migration season. And you also see the greenish parts, they are precipitations, which are originally designed to detect this precipitation, the storms. So what we have, we observed here is there are so many biological behaviors in this data, but over the past decades, only a tiny amount of data has been analyzed because you have to manually detect these patterns I'm gonna show later. So move forward, we focus on the tree swallow. This is one of the major migratory birds that has been in a steep decline, and there are thousands of million swallows aggregate in roost. So this is one of the major migratory birds in North America. And they have very, very interesting behavior. During their migration, they're gonna take a break over the night to have some food, to take a rest, and in the next morning, they fly away from this habitat. We call it a roost. So the roost is not the tiny cute roost on the tree. It's actually thousands of birds aggregated together in a field. So in the next morning, they fly away from their roost. And in a very interesting pattern, it's not a random fly away. They follow, they go up, they spread out, basically looks like a small tornado. And this unique pattern leaves a signature on radar. So as they move away from their roost, they spend, disperse, and give us this donut-like pattern. Then it becomes a computer vision problem. So if our principle to work on this kind of problem is if our human eyes can detect these patterns, then there's a good chance that computer vision models can do it as well. So again, radar data provides near complete description of the tree swallows. If we can detect these blobs in a large scale in North America, this continental scale, then we are able to monitor their migration, right? Because this is their signature. The challenge is we cannot manually annotate every single blobs because there are 200 million files collected in the past 20 years. So then this motivates our project. We want to develop an automatic system to detect and track the swallow roost over continental scale. So this is our motivation, very motivated. I'm very excited to work on this at the first year of my PhD. So now comes to the issue. What's the data, where is the data, how to collect the labels? This is always the most headache part. And fortunately, people have been working on this for decades, ornithologists. So what they help us is they have this radar data, the radar signals. There are many channels, like over 16 channels. But in computer vision, we always take RGB images, 3 channels. If we want to grab a well-established object detection model, we need 3 channels. So we ask the expert to pick 3 channels for us, the most important one, so that we can render RGB images. But later we actually show that we don't actually need to do that. We just feed all the channels and develop a new ML model to do that. So this is the input, and the right one is the output. We want to detect these blobs in the image, in a our radar image. So this bounding boxes is our output, our target output of our machine learning models. And you can tell that as people who are not familiar with, who are not working on ecology, it's impossible to annotate these patterns because it's not a perfect circle. We need ornithologists or PhD students who are working on bird migration, who are familiar with this, their patterns to help us do the annotation. So we cannot do this. We ask them for help to annotate them, these patterns. And fortunately, at the very beginning of this project, we don't have to do that. So in the past decades, people manually annotate over 60K roosts in 90K radar scans, and this gives us a warm start, right? We can let's see if we can train some object detection and tracking models on this small number of data and annotation and see what we have. Okay, then model development. This is most this is the most relaxed and probably easiest part for me. Once we have the data and the labels and we reformulate that the object detection and tracking models, I'm so comfortable to try many state-of-art computer vision models. So we already done the first part. We asked the experts to render RGB images for us. We grab some state-of-art object detection model called FastRCN. We got the detection because it's there's a sequence. The bird is there are some dynamics. So also develop some tracking and tracking models basically. And in the end, we have this tracked detections. Okay, very nice. So we're gonna skip that because that's very straightforward for us. We do model evaluation. And in computer vision, we're always obsessed with this leaderboard, right? We have scores, we want to compete and surpass the state of art. But sadly, the average precision score is very low for us, 9.1. We are so disappointing. We said, oh, probably this is not working. But if we realize the results, the form of animation actually came from our model. Our collaborators are super happy with this visualization. And they said it's impossible that this model is not working because visually is good. And that's one thing I really like computer vision. You got what you see, right? It works. You can see that. But the score is so low compared to the SOTA scores. Like in computer vision, we have a standard benchmark called the Pascal VOC. So the score is 78.8%, and we want to figure out why. So this is the issue we mentioned. Model evaluation doesn't work, so we'll go back to the early stage. We probably need more data, more label, or better annotations. And it turns out it's not an issue of the number of labels and the data. It's an issue of the annotation noise. So here is an illustration. When we annotate this image, what we want to get is this very unique, there's no ambiguity in annotating these images. But in practice, what do we find? Because this annotation collected from different research group, different users, and they have their own bias when annotating these images. For example, there are 3 users. One just put the bounding box on the top of the boundary. Another just titled the blobs. And the third one just loosely put a bounding box there. So this leads to results a lot of trouble for us in the evaluation and also the training, because there's no single standard policy to do the annotation. And what we do, then we are very comfortable with this. We develop a learning algorithm to learn from noisy labels, and we build a probability graphic model. We're gonna skip the technical part. Once we have this learning from noisy labels, we got this pretty good score, 4.8, and then we can write a paper. Okay, now the last part, most fun part. So this, once we have done the model evaluation, we're happy with the evaluation and we move forward. We also add more technical innovations later with my collaborators, Gustavo. And we deploy our system on 21 years of radar scans from 12 radar stations. And our AI system reduces human labors by over approximately 7 times. So our collaborators publish a lot of papers with our system to do some case study. Once we have the system, we can do bird migration, phenology, etc. And here I want to just give 2 examples I personally done in our paper. So once we've done that, as we mentioned, we can monitor the bird migration. So here the animation shows the bird migration in eastern US part from October to December. So during the winter, the birds are looking for some warm places, and you can see that they migrate to Florida, which is my dream when I was a PhD student at UMass. We can also study the habitat usage of these birds. And later, we also deployed the system to detect the bats. It seems the bats also have some interesting patterns. I cannot tell the difference, but our collaborators can tell. It's a magic to me. Okay, so this work is done with a big team across multiple institutes: Cornell, Colorado State University, University of Oklahoma, and UMass Amherst, when I was a PhD there. Large team. Okay, this is our first case study. The second one, very briefly, we're going to discuss the computer vision for material discovery. So also follow this pipeline, and our task is find the best zero light for a given application. Zero light is a widely used material in chemical industry. For example, they can do a hydrocarbon absorption. This is the only thing I know when I work on this. And it's very challenging to find one because they always have to do some physics-based simulation. It's very slow, like one material probably days to simulate to get the attributes of hydrocarbon absorption. So our idea is, why don't we just apply 3D computer vision? Because the input is basically, for us, we don't know what is this, but it looks like some 3D structure. And there are some correlations between this structure and some attributes, for example, hydrocarbon absorption attributes. So we developed this model named as ZeroNet, and it gave us good performance. Okay, this work is collaborating with chemical engineer at UMass. So as this is my last slide. As a summary, here is our pipeline to collaborate with people from other domains, computer vision plus X. And we find some challenges here. So motivation and task, computational communication barrier. Why do we want to work on this? Is this a computer vision problem? So my rule of thumb is if you can really detect the pattern, then there's a good chance that computer vision can help with the task. So what is the input and output? We need the experts, domain expert, to help us with that. And then the most common issue is the limited data annotations and noisy labels. So we can either ask a human to help us to clean up the data. We can also, as a computer science students and researchers, we are pretty good at building these annotation tools, web-based. And we can also develop some ML methods to solve this issue. And for model development and evaluation, my experience, we should always start from most mature computer vision models other than the most advanced one. So we have all got some feeders before because we are so ambitious to try the most recent transformer architectures. So that's all as a summary. The second parts, I show a general pipeline of computer vision plus X. We gave 2 case studies, how we collaborate with ecologists and people working on material discovery. And that's these slides summarize my talk today. Thanks for having me here.
Much, Zezhou. Okay, we have time for a couple questions in the room and then online. So any questions in the room? Amanda?
I mean, I just wanted, this is not so much a question as there's a large ecosystem of basically labeling efforts in astronomy called, one of them's Galaxy Zoo, but they're generally something zoo.
Right.
And so you have basically citizen scientists coming out and identifying things.
Right.
And you have heterogeneous labels.
Yeah.
big data sets. So just putting it out there.
Yeah, I think there's a lot of parallels that we'd be happy to discuss afterwards. Let's move on to a question real quick online, since I know we're going to have to end here in just a second. So let's just answer the questions online. We can finish up in the room afterwards. So there's a question about, can you tell us about how you ended up using all 16 channels in the end?
Oh, yes, that's a great question. So we simply add an adapter, which can take 6 channels as input, and we compress it to 3 channels and pretend we have RGB images so that we can use a pre-trained model that takes RGB image as input. So that's all, very simple one, but very effective.
Okay. There's another question about unsupervised feature extraction that's been maturing over the past few years. So could you talk a little bit about why you might want to or not use unsupervised feature
yes,
extraction?
I didn't cover this part, but in the materially described part, we actually use that. So especially since 2022-ish, I started working on self-supervised learning, unsupervised learning, and we tried that. So I didn't discuss that a lot here. But I think supervised learning is still the major success story in computer vision, even though we have some progress in unsupervised learning.
And I see that, Robert, you have your hand up. Do you want to unmute and ask your question?
Yes, can you hear me okay?
Yes.
Hi, so thanks very much. It was a fascinating talk. And I had a question about the tree swallow example of them, leaving in the morning in the roost.
Yes.
It looked to me that they disperse basically radially. Maybe it's a problem of scale or something, but they disperse radially beyond the detectability sensitivity of the radar, probably. But I missed kind of how this translates into the bark motion of migration.
Oh, yes. So remember I mentioned that during their migration, they migrate during the day, and over the night, they take a break, find some food, and in the next morning, they continue their journey. So we can't detect their stopover. And if we can connect this stopover, then we can get their migration path, right?
I see. Thanks, Awesome. That makes sense. Thank you.
Sure.
Okay, I think we're going to have to call it there, but thank you so much to both of our speakers. Thank you, Kelvin. Thank you, Zezhou. And as was mentioned in the chat, we'll have another seminar 2 weeks from now, same time, same Zoom link. So hope to see everybody there. Thanks so much.
Thank you.